Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our event tonight discussing retaining wall design with sleepers and panels. My name is Megan Purdy from Engineers Australia and I'll be your host for tonight's event. I'd also like to welcome our online audience watching this evening. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past and present. Now tonight we're presenting from Meanjin, home of the Turrbal and Yagara peoples. Before we get started, I would like to acknowledge that today's event has been hosted with Engineers Australia's industry partner, Brickworks. Brickworks is recognised globally as a leading manufacturer of quality building products, including bricks, blocks, retaining walls, pavers, natural stone, wool cladding, facade systems, roofing, and so much more. Our brands continue to build their reputation for delivering quality and lead the industry through style and product innovation, creating impressive materials designed for inspiring built environments. Now, in our session tonight, we will hear from our three speakers, followed by our live audience Q&A. So I encourage our audience in the room tonight to please get involved, and we'll have the roving mic and we'll bring it around and ask our speakers your questions. Okay. So I have the pleasure now of introducing our first speaker for tonight, Andrew Middleton. Andrew is a Senior Principal Geotechnical Engineer with 40 years practice in South East Queensland. After learning about soil behaviour, working on his father's black soil property and then graduating from UQ, his early career was spent learning more about soil and rock behaviour from great mentors on the infrastructure boom of the 80s and 90s that transformed South East Queensland with the construction of the Gateway Motorway North Side, Logan Motorway, Port of Brisbane, Gold Coast Rail Line, the Pacific Motorway upgrade, and then the South East Busway. From there, his mid-career experience leaned towards major land development and building projects, including the very first work at Springfield and the Gabba National Grandstand and Light Towers. With the latter part of his career spent learning more about soil and rock on a wide range of projects, working mainly for the owners, developers and builders seeking to provide practical understanding of the ground risks and solutions, particularly for marginal and poor quality land where he continues to learn. So please join me in welcoming Andrew Middleton.
Thank you, Megan. Thank you, Brickworks and Engineers Australia, for the opportunity to speak tonight. I am a practitioner, first and foremost. We've got a much more learned colleague to follow along behind, and he'll be able to probably give a little bit more. So I'm just going to give a bit of some introduction and then talk about some of the learnings I've had with some of the walls, retaining walls, sleeper walls as well. So that's good. So we just wanted to introduce at the outset, just talk about some of the advantages of post and panel or sleeper walls. So obviously it's a minimum land take. It's pretty much vertical. Tiered walls are starting to become more common, so there's a little bit of a land take compared to some of the alternatives. Staging, you can build it at the completion of bulk earthworks, which allows you, and it doesn't need a lot of room, so you can start construction of your warehouse or your residential, your civil works, whatever else. Speed, relative simplicity. One excavator, smaller work crew can be assembling these. Precast are just coming off trucks. Less working platform, say, compared to, say, a soldier pile wall option where you need quite high track pressures. Excavators, relatively simple, quite a lot safer to operate. Precast elements, obviously significant advantages where you're not having to cast on site. It does suit quite a range of ground types. Not all, sand, obviously sand, and we'll talk about fissured clays as well. So it's got a couple of limitations, but generally, as long as you can get the slopes to stand. Segue, short term, because of the speed of construction, the time frame that you would need a temporary excavation might be a few weeks. With some other systems, you might need, 8-10 weeks. And with pore pressure, obviously, pore pressure's soil suctions dissipate over time, and your temporary slopes may start to get into a point where you get more concerned about temporary stability. There's less exposure of workers to the slopes, depending on the way the system's built, but generally they can work away from the slope with the installation. So can be a better safety and design outcome compared to some other wall systems. The piers obviously provide some benefit in terms of global stability for a slope compared to, say, a mass gravity or some other ones. But that does have limits, and I'll talk about that briefly. And the other thing is, obviously, there are fewer failure modes to consider with sleeper walls compared to, say, gravity or some other wall systems. So I'll just briefly talk about that. So from AS 4678, there are those 8 failure modes you need to consider in your design. Obviously, sliding, not a factor. That's a factor for certain walls, but won't be a factor for those. Rotation, that is obviously considered. Component connection rupture, obviously with sleeper walls, you've got the connection or the interface between the sleeper and the post that you need to consider, and the bending capacity of the sleepers. There's obviously no anchors. Global instability, all walls need that checked. And again, rotation is a serviceability condition, translation and bulging, and settlement. So serviceability is pretty much common of just about all wall types. But you've simplified a couple of these and taken them out of the equation in terms of a risk for your construction and performance later on. Bit of earth pressure theory. I'm not sure, with combination of engineers and some. Simply, a Rankine earth pressure is a pretty common way to consider it. Coulomb includes, obviously, wall friction. You can't rely on wall friction in a sleeper wall because you've got a gap there, you've got drainage gravel. It would be a low friction. It's better to just simply use Rankine. Rankine theory, just Ka gamma H, pretty simple, where Ka, common form, has been around for many, many decades. And the practice generally is just to assume, rather than ignoring the tension zone, is to just adopt that, which allows for a few variabilities. And obviously with surcharge, you need to multiply surcharge by active to come up with your earth pressure theory. Might press that button. Soil cohesion and internal friction angle both feed into that. What's important to note is that active earth pressure does require movement. So you should expect that the wall will move to some amount to take up, to start from at-rest conditions, and as that soil relaxes, your pressure will drop from the active state down to the long-term, from the at-rest state to its active condition. So if you want zero movement, you need to design for at-rest conditions, which is a higher pressure, which means a stiffer wall, which means less movement. That's quite logical. It's up to 1%, but in practice, I'll talk about that in a minute, sorry. Soil parameter selection, it generally, the soil internal friction is generally relatively non-controversial. Selection of cohesion, though, can be, and as you can see in the fact that can be a significant contribution. So this is straight out of, obviously, the code. So your geotechnical practitioner should be giving you advice probably somewhere in this range. There might be special circumstances where they don't. And I'll talk about fissured soils in a moment. This, you can see generally, this Sorensen and Ockels, this is that plot there. There is considerable scatter. Your geotechnical engineer always puts in the report, soil is variable. Soil is variable. Right? So generally, there's going to be some judgment involved. There is always judgment involved in selection of parameters. That needs to be done with some caution, but also recognising it's got to be a practical design. It's got to be safe. Most Queensland soils tend to fall, so this is the plasticity index versus liquid limit. Most Queensland soils tend to fall in this range, which tends to put us up in this range, 26 to 30, which is somewhere in about this range. Most soils I see designed for are in this average. Some are a little bit lower. Occasionally you might get some out here, but most of the time you're in this range. I just wanted to talk briefly about fissured soils. Obviously this is probably a bit of a Southeast Queensland thing for everyone online, but nonetheless. Fissured soils have very low cohesion to no cohesion as well. Once you allow them to relax, they tend to drop any cohesion, the residual cohesion they may have had tends to drop away. Even in this is a local project, even in a soldier pile environment, you can see the soil arching is working up here in this zone where we've got the iron cementing. But as you get down here, there's less iron, and we've actually got these collapses over quite a small distance, and that's these soils over on the left. So that is always in tertiary. I've only ever encountered that in the tertiary soils in Brisbane, and it is not just in one. Someone might imagine it's only Raby Bay. It is in quite a number of places around Brisbane. You need to understand that. You can also evidence, this one is from the Corinda area, you can see those slickened sites. Obviously that's got quite a low cohesion, and you need to account for that in your design. I said before about the wall movements. What happens in practice, you design with your active earth pressure, and you say the movements could be up to 1%, but because you use safety factors, so you factor down your resisting loads and you factor up your applied loads if you're using limit stone, or if you're using working methods, you'll use a safety factor. In practice, that means walls don't usually get anywhere near 1%, but they're usually more than zero. So this was actually a case where we actually got to observe this behaviour, and what we found was this is chainage along, these are days, these are different chainages, and what we were able to observe was the time development of active earth pressure from the initial condition over about 100 to 150 days. So typically a geotech might say temporary slopes 4 to 6 weeks. This was a project where we actually got to see it in practice, and what it showed is that this part of the wall we got very little movement, but as we get further along the wall got higher and there became other water pressures involved, and we got movements approaching 1%. So. Sorry about that. Is that on, mate? Is that on? That's on. There we go. I'm sorry about that. So 1% is real. It can happen. It shouldn't, but it can happen. So you need to provision for that. If you've got a movement-sensitive circumstance, you probably need to design for K0. So these are in every good geotech report. They don't always get taken notice, but it's a real thing and it does happen. So, so the thing about sleeper walls then is that your load is developed from the earth pressures up here, as I showed you before. That applies a lateral load. So for a simple calculation, you can use Brom's theory. So this is Brom's theory for a C phi soil, where Kp is 1 plus sine phi and 1 minus sine phi. So that's your earth pressure. What happens is this load is actually, this graph that's been produced in here, you actually start at 2 CUD, not 9 CUD, square root Kp in the analysis. What I want you to see there is the resistance is very, very low at the surface. So if you're relying on high resistance early on, you can't do that. So, the thing also with Brom's, there's 2 failure modes you need to consider as geotechnical designers or designers. Short pile, where the pile deflects, rotates about a point of fixity. So we get resistance on the back, resistance on the front. You can see there's a lot of resistance developed in that circumstance. Long pile failure, where the bending capacity or the yield moment of the pile creates a failure or rupture in the pile. What you notice is there's not a lot of load capacity in that. So if you've got a pile that's slender, you're probably going to have a long pile failure, a lot of people design on this. You need to understand your failure modes and make sure that you have accounted for this correctly in your design. So what I just wanted to show is that for the long pile, for either undrained, but more likely frictional soils, when you look at the yield moments, you're generally down in these you've got relatively high eccentricity, and you've got a relative, what you end up with is, with your free edge, you end up with very, very low numbers, and you end up with very low resistance. These numbers are actually quite low, and they're a reason to be quite careful with your design and make sure you've understood and checked your failure modes. Just a couple other design. These have come all from practical experiences. Obviously, in front of the pile is you're highly reliant on resistance. You need to allow for surface trenches, subsoil drains. Reactive soils, if you're in highly reactive country, you'll get cracking develops in the top part of the profile. You need to account for loss of support. Where does the surface water go during construction? That's really important. I've seen cases where the surface water fully charges, overwhelms the wall drainage system, which is not designed for construction surface water, it's designed for seepage. That needs to be sealed. You need to direct your water away from your wall. Clay soils soften. If water sits there, the soil at the bottom is going to soften. The soil at the back is going to soften, and when the cohesion drops, the pressures go up. So need to take account. These really are something you need to be careful about with walls, and I've seen that exact situation. They just use 10 mil or crusher dust to backfill around the fiberglass shell. You've got a wall with the backfill behind it. Rainwater, surface, whatever, irrigation, you're watering of the yard. This gets full of water, then attempts to find its way to the outlet, which is the wall system, which wasn't really designed for this. This run could be 200 metres to the nearest outlet. If you've got a whole series of residential house lots, then this could be quite a long way. That seepage works its way through, causes softening here, increases the pressures here. And if you've got a reactive soil and you've got a house there, you could be leading to damage. So understanding what's happening here, if these are going to be involved, making sure all of this works properly and you get proper drainage is really quite important. And I just want to quickly touch on global stability. So this is just a classic limit equilibrium slip surface analysis. I have seen these where people just put in a nominal shear force. You can't develop shear force if the pile isn't embedded enough to get fixity. So one of the dangers of this pile here does nothing, so you may as well not have any contribution from it. This pile here has a short embedment, but certainly not what you would have designed the pile itself on. So when you're using this in analysis, you need to think about, for each of the slip surfaces you might be considering, don't just put a number in. Think about what the number means and make sure that it works, that the load past the system works. And I just want to finish on this. So tiered sleeper walls are just starting to see some of those coming through. Obviously, we need to level land. This is a design I've seen recently. This one happened to be in a weathered rock type subgrade, so it looks pretty right. But something to consider is that if you are considering a long pile failure, long pile concentrates a lot of load up here into the ground, right? Because if this is reached, these don't have a very high bending capacity. So what you need to do is make sure you design these properly and work out the contribution, because this system here is actually quite significant in resisting and providing a dual resistance. So this is actually a group action now. It's not just two individual piles. I've seen people trying to work this out and say, I'll do this, do that. It's actually a group, right? They're close enough to act as a group. They're in line with each other, so you're going to have load interactions and load and things. So you've got to consider your bending, your panels, your movements. You've got two walls now. That's quite a long. This one here. I think these are starting to get into the point where you're probably got to have to use finite element or Plaxis to try and understand how these are going to interact with each other to make sure they do work properly. So it really is soil structure interaction now. We're starting to talk more than just a simple, what I showed you before, which I think is a relatively simple way of approaching your design. These are starting to get in quite complex, complicated territory. And Bert, oh, sorry, Megan.
Thanks, Andrew. Back over there and go back to this mic, is that okay? Awesome. Thanks, Andrew, again for that presentation. Now I have the pleasure of welcoming our second speaker, Dr. Bert Look. Bert completed his master's degree at Imperial College London and his PhD part-time at the University of Queensland, while also working at Queensland Main Roads. He was previously, if I just turn my page, the global practice leader in SKM, now Jacobs, and also at Oricon. He was a previous director at FSG, Geotechnics and Foundations. Bert is the 2014 Queensland Professional Engineer of the Year and the Australian Geomechanics Society Practitioner 2018. He was awarded the Medal of the Order of Australia in 2020. He was recently awarded the 2025 Peter Hollingsworth Honoured Lecture by the Queensland chapter of the Australian Geomechanics Society. His latest book is Earthworks, Theory to Practice, Design and Construction. So please join me in welcoming Dr. Bert Look.
Thanks, Megan. Okay, now that Andrew's warmed up the wicket, I'll cover a bit of case study and I will also cover some theory to practice where you've been given a bit of theory and that's what you're taught at uni, but it doesn't work like that. So I need to bridge that. Well, it doesn't work like that even though, well, that's what you've been taught. So we're going to talk about some case studies. By the way, I got some questions last night. I looked at it this morning and I had hoped to update this slide, but unfortunately, a few tweaks which would have helped answer some of the questions that were online. I'm not able to because this is sent previously. Anyway, so we'll be talking about sleep retaining walls, and this is a colleague of mine who I asked him to take some photos over the weekend. That's his garden wall behind there, very nice looking wall, and nice plants, etc. So he's been living there about 8 years, and so that's his back wall, about 3 meters high in one area, and it drops off to the other end. Okay, now typically we think in terms of a classification of wall, where it's embedded or it's a gravity wall. An embedded wall, you put it in, you excavate, and then you have your embedded wall, and then there's a gravity wall. So those are the sort of classifications of walls. However, embedded, even though we talk about embedded retaining walls, there could be diaphragm walls, secant walls, contiguous sheet piles, king post, what is called king post and soda pile walls, and sleeper walls are just a subset of that. So you actually use it as a sort of in where I showed where there's backfill and you have something in front. You also use it in that scenario, even though you could have used it in deep excavations for the other types of embedded walls. It's just a subset of embedment walls. Pluses, very little space required. It's one of the thinnest walls, closely side boundaries. So you do optimize your real estate, so to speak. Now, again, another sort of classification has been around by Rook for 20, 30 years, and we see there's a lot of types of walls, and I've circled the type of walls of which theory was developed. So what you see is gravity walls. Back in the day, the Rankine and Coulomb didn't have embedment and digging and passive resistance, etc. It was all theoretical, and that's where we make our feeling, and that's where what you're taught at uni is actually quite not how it works, because they only knew the theories developed around a certain type of walls, and you see all the others are what we do today. So there's a bit of a mismatch here, and I'll take you through a few little, the king post, solar pile, sleeper walls, all subsets of that. We have to consider, of course, the active zone, passive zone, and Andrew's covered some of that. Bronze method, remember it's not just active passive, but again, Andrew covered that, so now that he's covered all of that. But within this solar power wall, we have arching if it's less than about 3D, but it could be 5D if it's rock, for instance, where you just have these solar piles, and then you fill it in the lagging, which is sleepers in between. And that lagging could be shotcrete, wood, concrete, steel sheeting, and of course, with sleeper walls here, we're talking mainly concrete, even though you could use timber and just, or spray it as for deeper walls. So generally speaking, you fit it in between upright solar, so to speak. If it was deep, you could actually put a H-pile concrete and put it behind it, so you could stiffen it up. But most things for landscaping is sort of this shallow sort of nature. But in Australia, we have to consider a few little nuances, which Andrew sort of mentioned, expansive clays, and this is where you need to neglect the crack zone for half times the HS, the suction zone, because things shrink, and when it shrinks, there's no contact. That's expansive clays. And half times the suction zone HS is typically the shrinkage depth. Then we also have to allow for future services, and typically it's 10% H or half meter, in case someone just happens to come and excavate in front of a wall. You've lost your passive pressure. So these are the sort of practicalities that one must consider in using these walls. So a few Australia-specific nuances and sort of general other things. Okay, so for sleeper walls, we have this active pressure at the top and a passive pressure below, in principle. Great for sleeper walls. That L should have been actually just between the two, I corrected that for my, between the two uprights there in plan. And that's for sleeper walls. But for continuous walls, which is if it was fully embedded, such as sheet piles, because that's a type of embedded walls, the passive pressure would be full depth, okay? And the active is full depth and the passive pressure just as before. But you notice the difference. One is fill-in, so the active pressure is actually just at the top, and the other one, if it had been a full embedment sheet pile, for instance, or secant contiguous, all these sort of things, and a diaphragm wall, it would be quite a different active pressure for the same principles. So we need to be careful of these little things. Okay, so let's just, how does this visually look? And I've tried to give you a bit of a GIF sort of thing. Say, suppose we had 4 meters medium dense sand and a typical embedment 2.5, and we have a very stiff clay. What you'll find is that you could see the arching effect and the active pressure being engaged on the right. So it's pushing against it. So the active pressure is being engaged. And so that is for a certain type of material of very stiff clay. What if we change the material from a very stiff clay? And let's just say, let's make it same medium dense sand. Look at what happens. The passive pressure is now being engaged. Before you didn't see that. So I don't know if I could go back here, but you notice there was no passive feeling modes of those wedges forming behind it. Those are the slip lines. That's a limit state analysis sort of approach, and it is showing all the various wedges and where it eventually, and then you have what is called an adequacy on strength of 1.11. If it's a stiff clay, we change it to another material, and the adequacy on strength is 0.98. In other words, it will fail because it hasn't satisfied the basic strength if you consider a limit state approach. And you can see the passive pressure being engaged here, but it wasn't in the other case. How it is in fact. I actually had another one which showed if we dug a trench in front of it, but that is not in this current version. So now that I've given you theory, Andrew's given it, here's a simple question from 60 years ago, 1960s. Casa Grande. Any one brave enough to answer a question, and I'm assuming all of you are engineers here who passed this exam. If you couldn't answer this question, you shouldn't have been an engineer in 1960. What is wrong with the way we teach? That's what the question is saying. We have these basic classical earth pressures, active and passive, and Casa Grande, who was in Harvard, was basically saying, well, actually, what is wrong with it? That's an exam question. And you should be able, as a practice engineer, know that the theory that you're being taught, which is what this question is all about, is actually wrong. So anybody, I've sort of actually said the answer. So you already have the theory, but it's important that you activate your brain, not just me telling you something for it to stick. So anybody I've actually said it. No one gave me enough. Okay, now that we know that you're all passive instead of active, what I said before was showed you the theories for gravity walls back 200 years ago. And that's what's wrong with it. It's outdated. It doesn't take care of the many walls we have today. We've stuck with the theory and applied it to the walls where it actually doesn't work like that. So I'll go a little deeper into this question. And what it is there's movement. Andrew said that. So if it's cantilever, it move about 0.5%. If it's proper tied back, different amounts. But depending on the soil condition, it could also move a bit differently. And you see these diagrams which are on the left about movements, etc. But if you notice, it always moves at the top. And that's what gravity walls did 200 years ago. They didn't have the walls where it could move at the base or slide. It was built as a solid gravity structure when they invented these theories. We don't do that anymore. Not in that one mode of failure, and Andrew covered there were several modes of failure. It doesn't take care of any of that. So if we move that forward a little bit, one of the things also because of this 0.5% or 1%, it's probably good to give it a bit of a lean back to compensate for the fact that it will be active and move. I mean, that's the whole idea of calling it active earth pressure. So if you know your wall is going to move, you maybe should kink it back a little bit. Not really applicable for short walls, 1 meter, etc. But as you go up, it becomes very important because then, theoretically, if you build it straight and it leans a bit, it's the same forces. But who likes to see a wall looking up at it, leaning over you? It's not going to feel comfortable, okay? And there's nothing in your analysis that says it's anything wrong for one versus the other. But we have said it's active, it's going to move. And Andrew showed you some of that movement that can occur. So let's just go through Australian standard on the left, and that is the active pressure, and you see again it move, and the passive pressure is where it pushes in, etc. So we have Ka and Kp, and here's run through sort of thing. But look on the left. If you notice, on the left, it's a triangle. But then if it shifts at the base, it's not a triangle. And if it's propped, it's sort of squiggly sort of things. All three are roughly the same pressure, but they are different points of application for the overturning part of it. And these are the walls, the second and third one. This is an Australian standard. It's sort of hidden in the back and it's telling you these pressures. So it's no longer triangular pressures, which we have for active and passive earth pressures. Nice theory stuff, but it doesn't quite work like that. And so this is in Australian standards for the past 20 plus years, showing you these pressures. It doesn't say how you get around these problems, but these are the realities of the walls that we do currently. So a bit of history. Coulomb, Rankine, 1857, and then Terzaghi, around 1930s, he actually wrote to his, and that's the founder of soil mechanics, wrote to the American Society of Soil Engineers, we should stop doing this BS, because it just doesn't work like that, sorry. But you know, something that's not quite right, but he called it fallacy of earth pressure. But keep in mind, these are the days of slide rules and no computers, calculators even. It was easy to calculate forces from a triangle. So we stuck with what was easy, not what's right. And it has become embedded in our system that we take the easy part, not what is correct to do. So the founder of soil mechanics said we should stop using Coulomb and etc. and Rankine. And in 2016, I do some courses on practice engineering, and I ask who uses Rankine earth pressures, and 42% people say yes. So there is hope that not everyone uses that blindly. So let's take a little bit of more depth of what that means. So this is on the left, straight out from a textbook, which says Terzaghi did not hold back and even wrote a paper describing the fundamental fallacy of earth pressure calculations, but with little effect, and the fallacy lives on. So we are happy to do the simple, incorrect thing rather than going to more complex things which might be correct. And this is our state of practice. Okay, now there are assumptions on friction, and that's not the key issue here, and how these things are formed. But what I need to show you is when to step back from these earth pressures that are taught to you, but actually it doesn't apply, not in that form anyway. So So this is 1930s, Tasagi, the founder of sound mechanics, having critique of that, and we've known that, and especially through FE studies, etc., we can show these sort of things. But let's look at the active pressure. And these are charts by Kakut and Kursel from much after Tasagi, and he shows the active pressure as compared to Rankine and Coulomb. And you see, for all practical purposes, depends on the friction and the Ka values. The two lines, or you can't even see, you only seen two, it's actually 3 lines, or 4 lines actually, 3 lines. There is very little difference. So if there's 10% error in the active, that's fine. So we are all good because 10% error when we have factor safety is not a big deal. So we accept errors. The fact it's wrong is not a big deal if it's only 10% error because usually we have factor of safety. However, embedment walls with passive pressure rely a lot on passive pressure. And remember, back in the 200 years ago, they didn't have an excavator to dig to get the passive pressure or to drill it or to push it in and to get that sort of feel. It was all gravity wall. So if we look at the passive pressure now, we start to see diversions of these curves from what we know as the truth versus Kakut and Kursel or Rankine or Coulomb. And they start to diverge, and roughly at about around 35 degrees, you need to stop using that and use these charts, which we have known for the past 50 years before most of you were born. Because Rankine will now have underestimated by 100% error, 100% in the passive zone. Remember, the active was okay. And Coulomb will overestimate by 20%. So we've known this for 50 years, but the university still stick to the basics. And we need to teach the basics. But as a practitioner, you need to go beyond that. So this is the key point that I'm trying to make here. Nothing of this is new, it's 50 years old. And teaching, unfortunately, has a bit of a conundrum. It needs to teach in a way which is not how it's used in practice. And so it's not a criticism of teaching, because they have to teach it that way, the simple way. And then later on you find out. And I'll give you a simple example of how teaching occurs. When you are in grade 1, every one of you, me, your children, everyone, is taught that you take away a small number from a big number. So for instance, you have 10, you can take away 5, that works. And in grade 1, 2, they tell you that. And they tell you, you cannot take away 10 from 5 in a subtraction. You could only take away the small number from the big number. Now that's how we were taught for years, but it's a lie. Because we all know with a credit card and a bank account, you can earn $100K and still owe $1 million. So you can take away a very big number. It doesn't make the method of teaching incorrect. You have to be taught that way, but it doesn't apply like that in practice. And so a lot of these things we are taught, I'm not trying to criticize how it's taught. I'm just trying to make sure that as practitioners, we know better, because the theory doesn't work like that. And these are things we've known for 50 years. Rankine and Coulomb has a problem at around 35 degrees, and especially for embedment walls, and at around 35 degrees, you start to get these sort of errors. So that's enough of theories, and again, what I'm going to show you is, again, on the left, well, my left, you can see how the earth pressure, if it moves to the top, it didn't move, okay, that's the at rest. It moves a little bit, that's the active. But if it moves to the base, it's going to relax. So the pressure relaxes at the toe. That didn't apply in the walls of the days of when they built these on good soil, etc. And similarly, when it slides, so where it moves to the base or it slides, the pressure releases, and it's no longer a triangular distribution. This is an Australian standard for the past 25 years. And it doesn't seem to be applied in practice. So what we did to correct the error is that if you have a factor of safety of, say, 1.5 for sliding, or at the top anyway, Tasagi says it's somewhere between 0.38 to 0.458. The pressure is the same, but the point of application of the moment goes up because it's no longer a triangle from the 1/3 centroid. So having moved up, if you think of it, 0.45 divided by 0.33 by typically 1.5 factor safety is 2. So when you apply a factor safety of 2 for overturning, you're correcting the error that you're doing the wrong thing. So it's a way we offset errors that are inbuilt into these equations. So don't use 1.5 for overturning, because your overturning is likely to be incorrect. And we don't know if it's going to slide, if it's going to move at the top, or if it's going to move at the base. The walls of the day from 200 years ago only moved masonry gravity only at the top. But walls today, with various configurations, move quite differently and could be any one of these permutations. Okay, so that's enough of what I call theory. One other last thing about theory, if you sometimes use walls as facing units, even in sleeper walls, etc., and it's not a full ranking unit pressure, it's actually just to prevent erosion. If it's, I think Andrew showed some of the soils there. If it phyllites, for instance, it might be weathering, and you don't want it to weather, so you put a wall as a facing unit to prevent that weathering, and that's all it is. So it's not an active earth pressure, it's just a facing unit, and one could use actually what is called a different earth pressure showing there for sort of a fascia wall. All right, okay, so let's look at a few things in practice. Shrinkage clays, and this was a particular case in Bohemia, 100 kilometers of rail line, up to a mine site, 25-year design. But this was where there were cracks observed in this shotcrete face, and that's because the sleeper wall moved. And what happened is that shrinkage cracks developed in the ground, and therefore there's loss of contact. If there's loss of contact, you cannot say the passive pressure starts from the surface and goes downwards. You've got to start the passive pressure at a lower level, below the crack zone. And that is a fundamental issue that still continues, all right? You do not use it from ground level, the passive pressure. Use it from, if it's expansive clays. If it's not, then it's fine. But if it is, and it's going to shrink and swell, when it shrinks away, there's no contact, so you cannot say it's actually resisting anything. So you've got to take that passive pressure starting from the base of that cracked zone. So typically a half HS, which HS is the sort of depth of the suction zone. Okay, so typical site, I'm not going to mention it. It's active. Some of you may have driven past it. And this is under construction, and you see things like people having lunch and vehicles parked there. The rollers there. And this is for a wall which is roughly 8 meters high at the peak. And this is what happens. But the pressures, the whole idea of passive pressure is when something rigid pushes against the soil. And when you compact or have something like that, there's a rigidity, and if the passive pressure is being invoked on the active side from compaction induced or just the load of that. So passive, active, and you can see that wedge there. Now, how does that affect in things in theory? Typically a 3 meter, let's say a 3 meter or 5 meter wall, you have an earth pressure of say 18 or 13 kPa, for roughly 6 H. So I've just used nominal numbers, Ka gamma H. And what we look at here is if you had this sort of compaction equipment, simple vibratory roller or smooth drum, 10 ton, etc. This is the sort of pressure that's been created. So in other words, by compacting the soil, and you want to compact the soil behind the wall, you're actually almost increasing the wall height by 2 meters from that compaction-induced pressure. So it doesn't give me any comfort when I've designed something and I see people parking there and they're using big rollers behind it. You are obligated behind a wall to use very light compaction equipment, vibratory rollers, or vibratory plate, but certainly not the 17-ton roller that has been used elsewhere, because it can induce, the wall needs to be designed for almost like a couple meters higher, which is what I'm trying to illustrate here with some of these pressures as compared to the equipment that would be used. So that's a practice that is not quite, it gives a bit of a heart throbs to designers when you see these things and you go out on site, because you know you haven't taken some of these things into consideration and you're relying on your factors of safety, your factors of sleep safety, okay? And then this is what happens in a typical Nexstar highway project. So here is a case, and Andrew gave a case of a tiered wall. This is a simple cantilever wall that has failed. You can see the sleepers, the concrete sleepers between, and some H sections, and part of it has failed, the other part is okay. And next to the house where we see that surcharge, you can see there's about a 600 mil displacement. That's part of the global stability. This wall was actually designed correctly, so let's not be critical of the designers in terms of what was required. But there's a bigger picture that occurs in global stability. As you notice, there's a creek down below. And global stability wasn't part of the assessment. And when you have global stability, you can see that the wall could be okay, but in this particular instance, the creek is eroding away that front part, which is actually part of the passive pressure. So let's just look at it diagrammatically, and what you see, the back of the wall, the depth of failure to the failure surface of the global stability, not the wall itself, which might be fine from all the analysis due to the limit equilibrium, but the creek eroding away, the base removes some of the soil keeps on moving, and then you've lost your passive pressure in front of this wall. So global stability is very important, and all that happened is that upstream of the creek, you had another construction development taking place. So of course, you know, water which would have gone through to the ground and naturally is now more runoff into the creek. The creek is not wide enough to take it, and your creek is eroding away, widening. And therefore, this wall, a bit more downstream, a few hundred meters downstream of where all these developments taking place, has now suffered because of somebody half a kilometer upstairs of huge developments. But it didn't mean it was incorrect initially. So this is an importance of global stability and understanding the big picture of walls, and this would apply to any wall, by the way. It doesn't necessarily see this wall, but all other walls would have lost its passive pressure, and these are the sort of considerations. Okay, and Humpty Dumpty had a great fall. So you can see what happens, the entire wall that fell down and the sleepers that are there. Okay, this is the end of it. I actually did have one or two other slides in between which would have helped to answer questions, but I think we are near the end here. And this guy is the greatest promoters of walls, and that Brickworks can never even touch him. Actually, there was a song track, Build a Wall, but you can't hear it now in this version, because I thought it was such a good theme music to end this. But in building this wall, build a wall, you're supposed to be hearing that song track right now, which is not in this version. Our Trumpian friend here would have also said, check for global stability, ultimate and stability conditions. So hopefully you understand that moving forward. And that's about it, and on to the next speaker. Yeah.
Thanks, Bert. Awesome, thank you so much. I'd now like to welcome our third speaker, Adam Ransley, Landscaping and Civil Manager at Brickworks. With a strong foundation in mining and civil construction, Adam brings a wealth of experience to his role at Brickworks Limited, Australia's leading brick manufacturer. After spending 8 years in the Hunter Valley's coal mining sector, Adam transitioned into Brickworks Masonry Division 5 years ago, where his passion for the civil market quickly took shape. Dedicated to the company's forward-thinking approach, Adam takes pride in Brickworks' ongoing commitment to strengthening Australia's building industry. The company's recent $300 million investment in 2 new production plants in New South Wales underscores its mission to innovate and expand, ensuring long-term success in the civil sector. Please join me in welcoming Adam Ransley.
Thank you, Megan. And thanks, Bert and Andrew. Appreciate your time. I'm Adam, and I am the Landscaping and Civil Manager at Brickworks. So the two blokes before me, they were speaking about, I guess, the pre-design of the walls. Our job at Brickworks is to supply the product that's going to be fit for purpose. And I'll talk about some of the scenarios that we see post-installation or pre and during installation. So those will be panels versus sleepers, the zone of influence, minimum embedment, quality product, and why Brickworks in our range. So panels versus sleepers. We're seeing a big trend in the market where we're seeing more panels being specified and used on site versus individual concrete sleepers. You can see here, those 1 metre by 2 metre long concrete panels that look like individual sleepers. So through the case studies, some of the differences we see in the differences between panels and sleepers is creepage. When installing single sleepers, we see a risk of higher creepage due to imperfections in production tolerances and installation procedures. So on the left there, you can see a concrete panel where it's nice and flush and all in situ. From there, on the other side of the concrete of the panel is individual sleepers, and you can see when installing individual ones, where you can start seeing creepages in the wall. Another case study we see is growth through the concrete sleepers. So they're individual sleepers, and you see when installing single sleepers, risk of the growth through the wall can be an eyesore and has the potential to lead to other implications such as post-installation sleeper movement and silt running down the face of the wall. Aesthetically not pleasing. Installation time. As retaining walls are normally one of the first tasks on major projects, our 2 metre by 1 metre panel is equivalent to 5 single sleepers. Installation time and labour costs have significant benefits to the customer's schedule and budget. Furthermore, 5 less lifts on site also reduces 5 less risks of pinch points. With WH&S being the #1 priority on site, panels offer a safer option for our installers. Another time we see from time to time, when installing multiple individual sleepers, bowing can present itself over time due to different load points in the wall. A panel will dissipate the load through a larger surface area, reducing the risk of wall dislocation. Since introducing panels into the market, Brickworks have had that 83% drop in complaints of bowing in retaining walls. The zone of influence. The zone of influence of a retaining wall is the area behind the wall where changes to ground conditions could affect the wall stability and performance. This area is critical for understanding the potential impact of structural loads and for designing the wall to withstand these loads safely. So this is an example of some of the things we see on site post-installation of the wall. That didn't work. So that's vibrating, compacted in the ground, and you see a lot of concrete cracking post that, which defects the panel. No fault to the installer, but could have implications to what happens to the wall down the track. Another issue we see on site is minimum embedment. One of the greatest risks to sleeper walls is installation imperfections around the minimum embedment of sleepers into posts. I see multiple projects that fail to meet the minimum requirements, resulting in lots of rectification work. If this occurs, replacing panels can be a lot cheaper option due to the lifting point on a panel, rather than removing 5 individual sleepers, which could potentially result in product damage. The number of rectifications have become so high that we're seeing a new trend in the market where we're having 150 UC posts being specified on projects versus the standard 100 UC, even on smaller walls, just to ensure that we get the embedment. So quality products. Ultra masonry concrete sleepers are manufactured to AS 3600. All reinforcing bars used for concrete sleepers are compliant with AS 4671. And Austral Masonry manufactures and sells products to a certified ISO 9001 quality management system. So here's an example of our production plant. So the reinforcement bars are on chairs. They're poured into moulds. From there it goes to vibrating and screening. It kills in a chamber and then removed once it hits its 60 MPa. So here's some examples that we see on site. So on your left, example A shows the correct location for the reinforcement bars. In example B and C, you can see the reinforcement bars during the production process aren't in their correct position. And if you look at C, the reinforcement bars are actually touching. This could lead to potential further problems on site that you don't see. So why Brickworks? We're 100% Australian owned with manufacturing facilities across all states. With a strong focus on sustainability and continuous operational improvement, we've made significant investments in setting ambitious targets to further reduce our environmental impact. We're passionate about collaborating on your projects, learning your vision and bringing them to life. And our team is committed to supporting you every step of the way. At Brickworks, our focus is on creating beautiful, durable products that stand the test of time. We're globally recognised as a leader in quality building products with brands that lead through style and product innovation. As an active member of Australia's vibrant design and construction community, we value your ongoing collaboration and dialogue. Your feedback helps shape the development of new products and services, ensuring we continue to meet evolving design and performance needs. At Brickworks, we're dedicated to building a greener, cleaner and more sustainable future. Since 2006, we've achieved a 56% reduction in Scope 1 and 2 emissions across our Australian operations. Currently, 11% of our manufacturing energy comes from renewable sources. So our concrete sleepers. Whoa. Okay. Our Explorer range. A simple system. Each sleeper has 2 reinforcement bars and 12. We have 75mm thick. We also have 100mm thick range too. Come in various different textures and colours. Our charcoal slate, graphite sandstone look, natural sandstone. Our timber look range in Gumtree, ironbark, charcoal smooth and grey smooth. Our panels are 2 metres long. They also have N12 bars running through each individual row with 8mm running vertical. Our concrete is poured at 40 MPa and has tested to cure over to 60 MPa. We have a design life of 60 years, a 35-year warranty, which is currently being updated to meet a 60-year warranty. Fence brackets for installing fences above the wall. That's our Explorer concrete slipper range. Thank you guys, appreciate your time.
Thanks a lot, Adam. And now if I could just get our speakers to come to the front of the room. It's now time for our audience Q&A. So let me just try and pull this off if I can. I got it. Awesome. So what I'll do, just a reminder to our audience, we've got this mic, so I'll be around in a sec. So please, if you've got a question, raise your hand. Don't forget to introduce yourself and indicate who your question is directed to. Do we have anyone who's ready with a question in the audience? Oh, they're all so shy. Lucky I came prepared with questions, if I can turn the page. So, very lucky we had people who registered for tonight and sent through their questions. So what I'll do is I'll kick off with some of those questions. One came through from Ivan in Queensland. And the question was to the panel, how does the industry, especially design and supplying companies, approach the design of tiered or stepped walls?
All right, but you have to answer next. I think for me, work needs to be done. I think there's, you could see Bert produce some finite element. I think we're getting to the point where we're going to need to use finite element for tiered walls. There's a lot going on. The simple, again, as Bert showed, there's simple methods for walls up to a certain point, but after that, they really, the theory doesn't really, it wasn't made for this, the territory we're getting into. So my view on that is, we're going to have to start throwing plexus and treat them like we do other big walls. And not just understand the loads and the limited, but also the movements and where is the stress coming on to the sleepers. So the sleepers have a certain capacity, bending capacity. They may need to be amended in some of these cases. So, anything to add?
Yeah, some trends we see in the market is like double paneling, triple paneling on walls to just as a safety net for that structural stability of that wall. We've seen that get specified a lot more. Yep.
Okay, I guess as a sort of like a guidance, the zone of influence is roughly 45 plus 5/2 for the active pressure. So, but let's make it simple and say 45 degrees. So if you have step back, the height of the wall is where the active zone is going to be. And I believe you showed twice that is where you're fairly confident the movement zone may still extend a little bit beyond that. So if you have twice the height, is probably where the next tier should be offset so that the active zone doesn't interact with the passive zone of the higher wall. But then you have to consider the other wall. The passive zone is what is called 45 plus 5/2, and it's now may cross over. So you have a vertical wall, you have an active zone, and you want to be not to interact with it. But this other wall has a passive zone in front of it, and those two interaction of the passive zone and the active zone should not interact. And Andrew mentioned that was actually not an FE analysis, that was called a limit state approach, just to illustrate the movement. But in that you could have seen illustratively that there was some shear surfaces up to where it occurred. It wasn't an FE, it was a simple limit equilibrium, limit state, not limit equilibrium, limit state approach. But, so those are, I guess, general broad guidelines.
Awesome.
Yep.
Thank you. Any questions from the floor? Oh, hold on. Oh, I'm coming.
Instead of double paneling or triple paneling, is it reasonable practice to maybe alternatively use no fines behind the wall?
In my experience, the nominal practice is definitely to double panel, and I think that's got to do with the price. It's quicker to do that, is my belief.
Yeah, I mean, price governs, so you're just driven up the price. Yep. Not to mention, I guess, depends on how the extent of the no fines. A lot of these walls, you want to plant things behind it. You're going to kill your plant not having a nice soil behind it. So you're taken away from the aesthetics and the trees that they want to plant because you have, I guess it depends on the width of that no fines. If it's narrow, I guess fair enough. But if you make it an entire block, you've removed, not having that in place.
Yeah, and I think there's probably a bending capacity consideration in that as well. So the no fines obviously has got no tense, but front face, back face. I'm not a structural engineer, studied it long enough, but double panelling obviously provides some benefit in terms of that. That lagging pressures that you're generating on those lower panels, although once it moves, the pressures drop off and you need the pressures up higher instead. So you can see there's a little bit in that, and my view is be conservative. These are big walls.
Yeah, I guess another point, even though the cost has gone up, you actually have reduced the active pressure because of, depends on the width of that block, to some extent, you have reduced that. So that may give you a bit more height as well too.
Any other questions? Oh, we'll go on over here. Hold on 2 seconds.
Hi guys. I just have a question in regards to what what are some of the most common failure methods that you've seen with regards to actual installation of concrete sleepers? As engineers, we design and we're pretty happy with our design, but when it actually goes out to construction, what are some of the issues you've encountered and how do you mitigate that?
So, just problems that we see on site. So, the ones I spoke about today, definitely minimum embedment is something that is usually picked up at the end of the job. So often people don't check that they had their posts in the right position at the installation point. And then when they don't hit that minimum embedment, and then trying to replace that at the end can be very, very costly. Where we're seeing a lot as reduced issues is using the panels versus concrete sleepers. More movements on site, higher risk of damage to those products. So the single installation of one panel, we're seeing a lot less issues regarding to product damage. Structurally, another thing we're seeing get specified a lot more is the bigger posts, especially with deeper piers. I guess when I first started, the rule of thumb was 1:1. We're seeing a big trend change where, say for a 1 metre high wall, it's usually 1.6 deep is what we're seeing now. So I'd say the market's definitely found what the big problems were, and they're overcompensating a lot on that in the installation process, for sure, but it's reducing the risk.
Yeah, you mentioned 1.6 meter deep for just 1 meter. That's overkill, especially if you're in weathered rock, for instance. You're having trouble digging, and it's so strong, and yet you keep on going. So yes, that number may apply for a certain soil condition, but every soil condition changes, and as I showed, the mode of failure also changes depending on the soil condition. And so really, that's a huge overkill. That certainly is applicable in certain weaker soils, but certainly not in the residual soils and weathered rock that's at least probably twice more than is required, yeah. Yep.
Any other questions? Oh.
Speaking of weathered rock, when posts are founding into weathered rock, what parameters should be considered?
You were showing the parameters.
I did. So the purpose of the parameters is to estimate the passive resistance correctly, isn't it? So what I do is look at obviously some cohesion, and that I think is a reasonable allowance for depending on the type of rock, and obviously a friction angle. There's plenty of guidance out there for friction angles for weathered rocks, so you can do that. Obviously, we're talking weathered rocks now. Obviously, the fresher the rock, you get you can have whatever passive resistance you want. It'll be hundreds and if not more of kPa. It becomes irrelevant. So, for in those more decomposed, if we're talking extremely or even highly weathered zones, cohesion is a judgment, right? It's the hardest part of the job in what we do is getting that about right. But I do, you can do a bit of sensitivity analysis and see if it often doesn't make a lot of difference. You still end up 1.6 versus 1.8. Well, from a builder's point of view, the cost is insignificant. So, err on the side of doing that. So, look, Geotech's been debating C5 forever and will continue to do so. It's just a way of estimating a number you think's right. Honestly, if you really want to know, go and put in a poll and test it. See, find out for yourself. If you think there's a value in a particular project, the walls are getting big, I think there's opportunity for testing and understanding what exactly is going on. So.
Okay, Andrew showed you some values there that it applies to soil, and the debate within Geotech is how much of that cohesion do you not use, because when it's strange, you lose that cohesion and you have a loss of cohesion in the long term, a reduced cohesion. So the C value should be reduced, and arguably a lot of people use 0. Now it's actually never 0, but it's a low number, and it could be as little as 5 now, or 10. But that depends on the soil condition. And we need to be careful here, certainly for firm clays and dung or that 0 is probably a reasonable number. But when you're up to very stiff and hard, a sort of a nominal 5 kPa is not unreasonable. And that cohesion actually does give you a lot of, grunt, so to speak, resistance. Now, one of the things is that 2/3 of wall is going to be built on residual soils and weathered rock. Now, rock actually has a cohesion which is not going to change because it has a cementation. So actually, the ability to use 10, 25 kPa there is very real because it doesn't have that cohesion reduction which soils has from straining, because rock has a natural bondage from a few million years of bonding. The soil didn't, and the soil has come from a transported past 10,000 years. And you can't compare the theories of cohesion reduction in the past 10,000 years versus something from 100 million years of bonding to get that cohesion. And unfortunately, there's a bit of extrapolation from transported soil to what is called sedimentary soils with those residual soils and extremely weathered rock, which has real cohesion that is not actually going to change that much. Even in a long term, you could use even using reduced values as compared to a Holocene sort of material where, yes, you should debatably use a low value.
Yeah. I don't think values of 15 to 25 are not uncommon to use. I don't think they're 10's too low if we're talking those weathered rocks. One other caveat though is fractured rocks. Obviously, you need to be careful that the weathering is actually quite good because you get some cohesive type behaviour. But obviously, if you get into fractured rocks, need to be careful there because obviously I'm sorry for everyone online. Fractured rocks, obviously, there's going to be movement, right? And then we're starting to talk about serviceability conditions. So you need to use some judgment there and probably downrate your parameters to try and limit movement rather than, you're not talking a limit state failure, now you're talking a serviceability condition. So judgment is required.
Any other questions from the floor? Yep.
Andrew will probably know me anyway. You met me before. Bert Luke will probably not know me, but I just pat on your back and say, I thought you retired. But knowledge, when you want to learn knowledge, right, it never ends till the day you are dead, okay? Now, I've got a couple of questions anyway to let the audience know is that we all know that AS4678, which is the 2002, is a document that we all got to be very careful because that document does not allow embedded wall. And that's where the flaw comes in because there's a lot of structural engineer out there doing a design based on what is stated in that code. It is wrong. The code refers to AS2159, which is a lateral load under a single pile. Now, being a geotechnical engineer, we all know that when it comes to embedded wall, you do not work out the active pressure and make it into a concentrated load and say it applies to a pile head. Because in embedded wall, there is a difference in pressure. Remember, you got an excavated face and a back, which is an active pressure, okay? So I'm very grateful that we have two geotechnical here, right, who understand about embedded wall. Because a lot of people that I've seen, okay, in my last 15 years of designing sleeper wall, that's what I specialize in anyway, 90% of them got it wrong. Absolutely wrong. They don't even know anything about geotechnical, and my advice to structural engineer, just be very careful, okay? I'll let you know about myself anyway. I'm actually 42 years experience. I'm graduated from Bendigo College of Advanced Education, old school. When I did my civil engineering, I have learned civil, structural and geotechnical. And I'm still practicing that, okay? And I run my own firm, okay? And I'm registered RPEQ in civil and structural. My advice to all of you out there, because the world is changing, a lot of people are very specialized. I specialize in structure, I specialize in geotechnical, I specialize in civil. And that's where the problem starts. Because we do not know that in the real life, a retaining wall consists of 3 disciplines: geotechnical, structural, and civil. Now, how does the civil come into display in this retaining wall? A lot of civil engineers don't give a damn about where they put the wall. All they do is just draw a wall, fill it up, and then forget about the overland flow, flood levels, and guess what? When the wall falls down, the geotechnical and the structure is the one who gets the blame, and they walk away. Well, thank God, I sit in a committee for CEE 032 in Standard Australia. I just drafted with my colleague for Chapter 8, Embedded Walls. And I have also revised and edited a Chapter 5 on drainage to make sure it's so robust. When the new code comes out, the civil engineers, you better watch out. Don't just put a wall and draw a line there, because there's a lot of things in there that you will be responsible. Thank you.
Thank you. I did have a question which came through from Napesh, and it was with regards to, with the change from the sandstone retaining walls to the concrete sleepers, how much load reduction do we expect from it, and will it help to reduce the separation required for any bridging design required for the Bonnery job? No? Okay, I can move on to the next one then. Not a problem. Moving from sandstone. We might leave that one then. Do we have any other questions from the audience? Oh, I've got one. I've got another one. Hopefully this one will be better. This one came in from Jackson. What are the control or management measures for tree roots or impacts due to nearby vegetation which cannot be trimmed due to environmental restrictions?
I've always
They've
had problem with
learned.
that. I guess, yeah, it's very, very important thing that we can't cut the tree, we can't do anything, and the tree for, you know, we put barriers to prevent rock falls. When the root of the tree is dislodging a wedge of rock, it'd be cheaper to remove the tree and plant 1,000 trees for the cost of the retention system that prevents a tree which no one planted, just the bird drop-ins, and it's now going into cracks of rocks, etc., and it's dropping off wedges, and we are putting walls or different retention barriers. But on a personal note, for instance, I had a palm tree of 5 or 6 meters away at my house, and I had this sort of wall which it came through, but it actually, the wall was on the edge of it was around an area that I concreted, and the roots actually came through above the concrete, but some also went below to some other areas of pavings, and every 3 years I had to adjust the entire pavings near my closed line. And seriously, every few years, it just shows you that this was about 5 meters away from a tree in a non-expansive clay area. So it's not to say that you have in movement, it's simply the tree roots do cause that. And I remember a particular incident of where I have a copper's sleep log, sorry, coppers. And I stacked it up close to a lime tree I had, trying to, when I built a pool, and the roots actually went under the sleeper wall and came up, and it was disturbing the pavers, and the pavers would drop in because the tree root came under, and again, I had to reset everything, and in fact, it broke the pipe in at one point. So the tree roots can, in this case, in front of the wall, came under and up, and created an issue for, this is for a simple 700 mil wall or whatever it was, just a handyman's job. So yes, it's important that we do consider the effect of trees, which can have up to the drip line, the roots will extend, and even more so, of course, if it's reactive clays, it will go even further, but even non-reactive, it does create an issue which needs to be designed for.
Red jacking is a large force. Nature never sleeps. We do. Never stops. Same as seepage. It never stops. I haven't got a specific answer, but just thinking through how would I address it if it came to me. And obviously root barrier stops the progression of the roots, but obviously there's still a jacking force on there. So there may be some potential solutions around using vertical void formers or some other media. On the wall side of the root barriers, it might just allow a bit more accommodation. But at the end of the day, a tree's going to keep growing. I mean, so it's eventually going to affect the serviceability of the wall. So yeah, there might be some simple practical things that you can help at least mitigate that and reduce the timing of when you might reach that point where you're just going to have to pull the wall down and build something a bit differently. So
Awesome.
Horticulturists might know a lot more than that too about how to stop
Thank
trees
you.
growing.
Well, look, final question I might pose to all of you, just your, I suppose, key takeaways from tonight. Start, Andrew.
Oh, okay, question without notice. Hardest question of the night. I think, so again, there are ways to design them, but we are getting into an area where the walls are getting much bigger, tiering. These are starting to get to what has always worked to now. We are now into territory where these are much more complicated. You can see there's a lot of product development going on. I think there's work that's got to be done. But shown ways you can analyse this to get a better understanding of how all this, but it is now really getting to what I call the soil structure interaction space. And excellent point. You can't, when you're starting to talk these, you need your good structure, competent structural engineer, competent civil engineer, and to be honest, you need a good contractor to be talking to. How are we going to build this? How are we going to maintain it? What's, whole of life, just looking at that together. So, but that's what good design is anyway.
Bert.
Okay, I guess I'm just, one of the questions that, and this caught my eye, so one of the guys, Morgana, I think was question 3 or 4. Just because I happen to know him, his question was there.
Fair
and
enough.
he asked about design life, and it's an important aspect of a wall, of anything, in fact. And I guess it depends on the type of things. Most housing developments, about 50 years is suitable. But then when we come to infrastructure, we're talking about 90, and the Australian standards do tell you this, minor infrastructure 90 years, and major infrastructure 110 years. Now, none of us are going to be around for that. So it's a bit of a guesswork of making those numbers, and arguably, none of us can actually say what it is. And yes, AS 4678, and the point was made for embedded walls, actually it doesn't apply. We need things like CEREA publications, which I refer to. It just has no guidance whatsoever on some of these things. But the Australian standard gives you design life for some of those. And if it's corrosion, for instance, the corrosion life for steel things, this is not specifically sleeper walls or geogrid, the creep factor to reduce for if it's 50 years or 100 years. And I guess it's answering to that question, but the key takeaway, we have standards for design life, and we have a standard that doesn't apply for walls, which are very common, a point that was made earlier by our colleague there. So design life is a very important aspect, and yet none of us are going to be alive to see if we are right or wrong. And I find that a bit disconcerting.
I think my takeaway is it's forever evolving. Like retaining walls have been around since like I guess Machu Picchu, and just my 5 years in the company, just the evolution we've seen. As I said, bigger pier depths, the panel versus the sleeper, bigger posts, stronger concrete, thicker concrete. Bigger reinforcement. It's always evolving, and your feedback really helps us drive that to a standard. It's our reputation on the line at the end of the day that we want to make sure that we put out the best product in the market, and we like to work in with you guys to make sure that it's your reputation too in designing the wall. So it's a collaborative thing for us, and we want to make sure that we might not be around, but we hopefully that they are around post our time.
Awesome. Thank you. Thank you all for, well, if I can say, please join me in once again thanking Andrew Middleton, Dr. Bert Look and Adam Ransley for their time and input tonight. I would also like to thank Engineers Australia's industry partner Brickworks for their support and for making this event happen. Once more, we extend our thanks to your presence tonight and to our online audience. For those in the room, we invite you to stay, network with your colleagues as well as some of our industry representatives. So please feel free to stay and make the most of this opportunity. To our online audience and to everyone here, good night and thank you very much.